So, hello everyone, and thanks for attending. Today I'm going to speak about how to write a Kubernetes controller with Go. The reason why I proposed this talk was because when I started working on Kubernetes more or less 1 year ago, it was easy in the beginning adding piece of code to existing projects. But as soon as I had to write my own controller, I found some issues in wrapping my head around how to do it. So that's why I thought it was interesting to others to speak about this. First of all, some quick words about me. I'm Federico. I work for Red Hat. Before that, I was doing distributed systems in the field of finance for quite a long time. I'm now part of the CNF networking team where we contribute to make it possible to run network functions inside OpenShift. And also I'm passionate about open source. My Twitter handle, my GitHub handle are FedePaol. Those are my emails. If you want to give feedback or ask questions or anything, just reach me out there. Normally here I would ask who knows what Kubernetes is, but given I can't see the hands, I'll just introduce it for those who don't know what it is. Kubernetes is a container orchestration system. Initially released by Google and now part of the CNCF. It's an orchestration system where you can run your containerized applications and it will make sure they scale, they run, they are healthy, they are spawn across different nodes and this kind of stuff. And Kubernetes is quite popular nowadays. So let's see how it works. Starting with the model, how it works. The first thing we should know is that Kubernetes works in a declarative way, meaning that you don't send command to the cluster. What you do is to ask the cluster to reach a given state. You declare the state you want the cluster to reach, and then the cluster will react accordingly and try to reach the state you're asking for. So, for example, this is probably the most abused example, the replica set, where you run 3 pods. A pod is the minimum running unit where you put your container. And here we ask for 3 replicas. And then the cluster reacts accordingly and spawns 3 pod. Then, at some time, you ask the number of replicas to be 2. And then, again, you're not sending a command to remove 1 pod. You are sending a new state where you ask for 2 pods. And the system reacts and removes a pod. So we can think about the cluster as a dynamic system, which at some point reaches an equilibrium. Then something happens, an external event or an internal one, and then a lot of events are from inside the cluster, and some controller react in some way and generate a new event until the equilibrium is reached again. So, for example, you can have one controller that sends, writes something in the storage of the cluster. That something is received by another controller that does something else and something else and something else. So it's a dynamic system. Is the right way to describe it. Everything sounds so cool, but there are complications. You know, a smooth C never made a skilled sailor, so we can say that a network without errors never made a system reliable. And what are the complications? The first one is that the storage is shared among all the components writing data to it. So what can happen is that you can have conflicts. And the way we handle conflict, the way the cluster handle conflicts, is that it implements a sort of optimistic concurrency. That's done because the number of reads are expected to be a lot more than the number of writes, and what happens when you have a conflict is that the second controller receives an error and it's asked to retry the write. And this is good for performances because you don't have mutexes, but the downside of it is that all the retry logic must be implemented in the client whenever it gets an error. So it's some kind of complexity that is removed from the cluster but is added to our controllers. The other thing is we can have missed events. It's a distributed system. Network is not reliable. Clusters and nodes are spawned across geographic areas, and also pods can die because of a panic in our code, or even because the resources are not available anymore, and even nodes can die. It's like just machines, so they can disappear. So how do we deal with missed events? There are two ways to handle this kind of stuff. So let's imagine that we have the number of replicas that moves from 0 to 1 to 0 to 2. And how do we deal with this kind of variation? There are two ways to deal with it. One is what's called edge-driven, meaning that we focus on the variation at the edges, from where the number goes from 0 to 1, from 1 to 0, or from 0 to 2. And in this kind of implementation, our behavior depends on the variation of the data we see at the edges. But again, we said that we could miss events, so this is not probably the most ideal way to handle that. Another way is that the one called level-driven. So in this kind of scenario, we kind of constantly are notified of the level of the value at any given time, and this is only what our controller should care of. So it's like constantly polling for the desired state and do something to implement our logic based on that desired state. Again, this is probably better because there are no events anymore, but it's not totally efficient. So the final solution is what they call edge-driven but edge-trigger but level-driven, meaning that it's just a fancy way to say you should implement your logic based on the global cluster state, but the point where you check the state is on the edges, because there is where you have the variations. So it's just a fancy way to say you should focus on the cluster state, but you can do those checks when you receive events. And this, after like 10 minutes, is probably the most important thing that I'm going to say today. But yet, we want to implement controllers, so let's move on to Kubernetes type. In Kubernetes, there is no black magic. It's just data stored in the storage, key value, and exposed by API. A Kubernetes type is identified by some parts. One is the API group, the other is the version, and the other is the resource. And the type is identified by REST URL. The type returned by REST URL is known as kind. And many Kubernetes kinds share some common traits. This is the Go struct of a pod. In Kubernetes, there is an extensive use of struct embedding. You can see it all over the place. And here we have meta, which is common to all the types and contains some information about the kind. about the type, the kind, and the API version. And then there is object method that is common to all the Kubernetes object. It contains informations common to all the objects, like the name, the namespace, and other informations. And then there are spec and status. It's a convention, but it's like used in every Kubernetes object I've seen so far. And the idea is that spec is the part where the user asks for the desired state. When this happens, the controller receives the change, then interacts with the outer world in some way, and then it reports back the status. So spec is for the user to ask for a desired state, and status is the way the controller reports back what is happening on the other side. And the other side can be something in the cluster, like other resources like pods for the replica set, or something completely outside the cluster, some IoT or your fridge, something like that. So let's see how to interact with this, how to implement it in Go. In the beginning, I thought that client Go was a client for like the same for each type, but the reality is that there is no such thing as a Go client. Client Go is more like a framework. Each type belongs to a group. For example, pod belongs to core, daemon set belongs to apps, network policy belongs to networking, and each API group has its own client. And all of them are collected together in a client set. Okay, and the client set is the object that allows you to interact with the cluster. So back again to the original question, how do I get a pod? In Go, the first thing you have to get is the client set, and you do that by passing it the coordinates of the cluster. It can be done using a kubeconfig file, or there are other ways if your controller is running inside a pod, but at the end of the day you get the client set and you use it for interacting with the cluster. And there are basically, through the client set you get the API group, and then you get the specific resource you want. You can interact with collections via the list method, for example, or you can interact with the punctual resources using the name. The verbs, the actions, you can use what you would expect from a REST client, plus there is this watch method, which is particularly interesting because it's the one that allows us to be notified about events. Watch returns a watch.interface, which is pretty simple. It has a method to get a channel where you receive events, and events are events containing some object. This is a way to get notified by events, but it's pretty low level. It doesn't handle errors for us, it's only the event-driven part. So what we should use is another construct, which is informers. Informers are a bit more higher level. On the cluster side, the informer uses watches to get notified of events. It stores them in a local cache that can be queried by our client, and it also allows us to put event handlers to get notified of those events. And on top of that, informers handles reconnections and failures for us, so it's slightly better. This is not the one you should use. The one we should really use is shared informers. Shared informers is yet a higher level construct, and the difference is that if you use many shared informers in the same process, they will share the same connection through the API server for the same object. So you watch once, you put less burden on the API server, and you can add as many handlers you want. And yeah, This is how you instantiate it, and how you add handlers, and how to interact with the local cache. One thing worth noticing is that you don't own the objects passed by the handler, so you are not allowed to modify them. The final piece of the puzzle is work queues. GoClient provides a priority queue that fits pretty well to the Kubernetes pattern. There are several reasons why we want to do that. We want to decouple the callbacks from where we consume the items. This is particularly true in case of shared informats, because we don't want to block the callback. And also work queues allows us to squash all the variations of the same object, as we are going to see in a few slides. The interface is like what you would expect from a priority queue. The only difference is the done method that allows you to notify that the queue that you are done with that particular element. The way it works is that from the handler we only store the key of the event in the queue, and then on the consuming side we can have many go routines consuming, so you can have a higher concurrency. And the good part of the queue is that you can add the same key as many times as you want. It won't be queued if an element is already in the queue. And if an element is being treated by a go routine and then the same element is put on the queue, then when that go routine calls done, that element was marked as dirty and it will be put again in the queue. This guarantees that different occurrences of the same event don't go to different go routines, which is pretty important because you don't want that one event to surpass another. There is another variation of rate limiting of work queues, which is rate limiting, which has another method, add rate limited, which allows us to put a key back to an element back to the queue. And in that case, the queue will re-emit the element following some rate limiting policy. The default one is some exponential backoff mechanism, and this is particularly useful for error retry. So, for example, if an element fails to be processed by when it's getting consumed, then what you can do is to put it back to the queue, and then after some time it will be processed again. And this is useful for failures for configs in the etcd, for example, as I said before. So, putting everything together, the first thing we want to do is to set the informer and the queue. This is how you get the informer of your specific type, then you add the handler. In the handler, the only thing you care about is getting the queue and the key and putting the key on the queue, and then this is how you do it. And then you also want, before like launching the consumers, you want to be sure that the cache is synced. This is because when you consume the key, you want to be able to fetch the content related to the key from the local cache. On the other side, reading from the queue, you just get the element. You want to call done whenever you finish processing it. You retrieve the key, casting it to a string. This fail should never happen. I'm not always confident in writing this should never happen in a piece of code in a comment, but this is an example, so it's fine. And then you handle it. If some errors happen, then you put the key back to the queue and then call it a day. And then the queue will handle the retry for us. how we handle the key. We split the key in namespace and name, and then the first thing we do is to retrieve the real object. And then when we are good, we ask the queue to forget about the object because everything is fine and we are happy and we processed the element successfully. So until now I spoke about like native resources, but the good thing is that we can do also this stuff for custom types. The addition of custom types made it possible to extend the Kubernetes behavior and write applications that fit that environment pretty well. So it's application written to run on Kubernetes using the Kubernetes APIs. And without those, it would be like having an iPhone without any apps. It would be a closed system with no much extensibility. The first thing we need is custom resource definitions, which is kind of a meta type. It's a Kubernetes type that describes other types, and it allows us to add more stuff on a cluster. And the way it looks like, it's like yet another manifest with a name and stuff like that, and fields that describe how the type looks like. So what fields it has, and the types, how that particular type should be rendered and stuff like that. And it would also be nice if all the commodities I spoke about before, like using informers, using type-safe client, were available also for these special types. And this is true because ClientGo comes with a code generator that allows us to generate some niceties for us. So for example, the deep copy method, it allows also to generate a client set, to generate informers and listers. It's a bit tricky if you're using Go mods, but it generates a lot of code for us while we are waiting for templates. There are mostly two particular files that we should care about. The structure the code generator expects is like this, and in doc you should put like package-wise settings. It's the way you instruct the code generator. So for example, here we say that we should generate the deep copy at package level. We declare what the group is and stuff like that. And then for types, we have type-specific arguments. Gen client asks for generating the informers and the clients and the listers, and then you can add other options. So if you want to write your own controller and take inspiration from something, the sample controller is the right starting point. But if you don't want all the ceremony, code generation, and all the stuff we discussed, ClientGo comes also with a dynamic client. By using that, we are giving up all the safety net provided by type safety, but it has some advantages. By using the dynamic client, you are not adding new dependencies, but objects are all maps between string and interface, and arrays are all slices of interfaces. It's like writing JavaScript. Nobody wants to write JavaScript, but it is what it is. This is how you use it. The hard part is not how to retrieve the object, but how to navigate it, because at each level you have to fetch the element from the map, see if it exists, see if it's of the right type, and then go down to the tree for each level. The dynamic client comes also with this unstructured package, which allows us to navigate a little better without all those error-prone activities. But again, it's something pretty tricky, and more risky, I would say. But again, if you have something where you don't want, you don't have the generated code, or you don't want to bring in another dependency, is another option. And then there are operators. Operators are, to me, are also a even higher level construct. Operator SDK is a framework that comes with a CLI that does a lot of code generation for us. It allows us to generate the whole project layout, to add new types, and even to write to generate the controller code for those types. All of these like in a code generated fashion. Also, the way the operators work is slightly different from how the controllers works. Operators rely on the concept of a primary CR, which is written by the user. Then the event is read by the operator. The operator then creates a secondary CR, and also it establishes an ownership relationship between the primary CR and the secondary CR. And this allows the cluster to garbage collect the secondary one whenever the primary one is deleted. And the difference between this approach and the controller I explained before is that in case of operators, whenever a change happens in the secondary CR, then the operator gets notified of an event on the primary one, and then it's due to the operator to retrieve the secondary one. So the entry point is always the primary CR. You can implement this pattern even with bare controllers, but in the operators is the way the generated code works. This is how you implement it. You put a watcher on the primary CR, in this case sample, and then you put a watcher on the secondary one, saying that you are interested in receiving events on the owner type. And this is the control loop, the reconciliation loop. So the event is on the sample type. The first thing you have to do is to retrieve it. Then you want to generate the secondary one, and then put the controller reference on it. Given that your entry point is always the primary CR, your code has to be idempotent. It can happen that some other events is happening on the primary CR, and then the pod is already there, which is the reason why we check for it existent. If it doesn't exist, we create it. If there is some kind of error, we throw the error and it will result in retrying. There are also other ways to force a retry. Requeue parameter of the result is the one you are looking for. Operators comes also with not only the controller code generation, but also some other nice features. There is this operator lifecycle manager that allows us to handle and declare dependencies between controllers, how to run upgrades. There is an operator marketplace, which is operatorhub.io, and operators also supports multi-tenancy. So operators are really a bit more than just a control loop. So wrapping up, the thing is, distributed systems are pretty hard. Failures are normals, errors are normals, and races are just behind the corner. The Kubernetes community came up with a series of battle-tested, well-established patterns. If you think that like implementing your own or doing polling or handling some special cases is a good idea, think about when your controller complexity will grow and with that the number of events and types it will have to handle. And think about the fact that corner keys are just behind the corner waiting for us. So the general message is stick with the patterns because they work, and even if you need to implement a bit more logic there, they are safe and stable. And this is what I had for you today. If there are any questions, feel free to write me or ping me in any way you want. And this link on the top is a pretty nice sum up of what I just described.